All right, so now in part 2, we're going to prove the decomposition in terms of generalized eigenspaces of T. And remember, this is for a complex vector space. And we're going to go ahead and do this proof by induction on the dimension of the vector space. Okay, so let's start with the basis case. Let n equals 1, so we've got a one-dimensional vector space. And then in this case, V is going to be the eigenspace of that first eigenvalue, which is a special case of the generalized eigenspace. And we know this because T has an eigenvalue by 521, again because we're over a complex vector space, so that's ensured. Okay, so now let n be strictly greater than 1, and suppose that A holds for vector spaces U with dimension of U strictly less than n. Okay, so for any vector space less than n, we assume the hypothesis holds, with the hypothesis being that this kind of a decomposition holds for U. All right, now since T has an eigenvalue lambda 1 by 520 again, we can write V as the generalized eigenspace for lambda 1 plus whatever else. Okay, so now if we'll call whatever else, we'll just call it U. Now the idea here is we're going to use this to reduce to our inductive hypothesis, right? So we're going to show that this guy here has dimension strictly less than n, and then apply that inductive hypothesis to this U right here. So just to work out the details, let's break down what U in fact is. So U is the null space of T minus lambda 1 I raised to the power n, and this here follows by 8.11, and then we say, what is U? Well, we've got this other result that says that for any operator, V is the direct sum of the null space of it raised to the dimension plus the range of it raised to the dimension. So since we've got the null space, then the other thing here, the other direct summand, must be the range of T minus lambda 1 I raised to the dimension. And so that part there, that's by 8.5. Okay, so now let's see. So then now we know that U must be the range of T minus lambda I to the n. And so then this one is invariant by by 820, our lemma. And the significance here of it being being invariant is that the operator restricted to U is defined. So if you go back and you check the fine print for the restriction of an operator back in 514, it requires that you have an invariant subspace, otherwise it doesn't make sense. And we also have that the dimension of this generalized eigenspace is at least 1, And so now that implies that the dimension of U is strictly less than n. So now we've verified that the inductive hypothesis applies. Okay. And what does that mean? That means that U must be a direct sum of generalized eigenspaces of restricted operators. That looks like this. So now the only thing that remains to show is we need to see that the generalized eigenspace of the restricted operator is the same thing as the generalized eigenspace of the full operator. Okay, so that's going to be a double containment, and the forward containment is more or less obvious because we know that the domain of T restricted to U is a subset of the domain of T. Now, for the other direction, suppose we take something from the kth generalized eigenspace of T. Okay, we want to see that it's in the generalized eigenspace of T restricted to U. Well, by 8.22, we can take our vector v and we can write it as v1 plus u, where v1 is in the first generalized eigenspace and u is in our leftover chunk u. And we can make that a little bit more precise, say, okay, so u is going to be v1 plus da 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 da, oh, sorry, v2 plus da 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 vm, where each vj is in g lambda j by our inductive hypothesis of T restricted to U. Yeah? And now we can use the containment of these guys. So then, since g lambda k of the restricted operator is contained in g lambda k of T, this decomposition that we just wrote down with v1 plus v2 plus up to vm, we can see that this first part here is an element of g lambda 1, and then this other part here, this is going to be in u. So now this implies that Vj is equal to 0 for j not equal to k by 8.13, which is the independence of eigenvalues yet again. So that means, so the independence then tells us that all of these other guys have to drop out, leaving behind only the kth one. And so then we get that v is equal to vk, but we know that vk is in g lambda k T restricted to U. So we just have to kind of chop away all the extra stuff so that we can see. So now that we're down on the level of vectors, we're back in the appropriate subspace. That's the summary of that one right there. Okay, so in other words, let me just point to explain this last part, because it's a little bit funky. The question we're looking at here is if W is a generalized eigenvector of T restricted to U, is it also a generalized eigenvector of T? So this is the question that you get by looking, sort of restricting your attention to just some subspace. And you say, hey, if things work there, then what happens when we throw in the rest of the vector space? Are things still behaving? And the answer is yes, because things acting under T stay in their own respective generalized eigenspaces.